Can you message me back? I cannot find you.
Recording.
Yeah, yeah.
Lecture 2 now I don't have any issues. But lecture 3 for sure.
Okay. By the way, don't tell this to anyone.
Hmm?
Don't tell this to anyone, please.
Yeah, sure. Okay.
Okay. Did you guys get the notification? The announcement? The grading and also the announcement? My office hours, I put in if everyone wants to. Yeah, can you go to the announcement? Yeah, put the announcement. There is no announcement. Okay, let me check.
Okay, so we are looking at October 15th as our midterm.
Oh,
Most probably on lecture 1, 2, 4, or 5, depending on how much we can make progress. So October 15th, Tuesday in class, our midterm. Yeah. Okay, so let's start. Today we are going to talk about power consumption of in CMOS inverter, and whatever we discuss, like all other issues, this also will be relevant to any CMOS logic circuit. Inverter is just an example. So we want to basically first see what are the different types or sources of power consumption that is present in CMOS logic circuit or inverter. The first one is called dynamic power consumption, and it is due to the charging and discharging of the capacitors that is inside the logic circuit, particularly coming from the transistor and the wires inside the logic circuit. The second one is called short circuit power. During the transition, as we can see from the voltage transfer characteristics of inverter, during the transition, there is a transition period when both transistors are on. There is a direct short circuit from battery to supply to ground that will give rise to some power consumption that is called short circuit power. And then static power due to leakage. When the circuit is at steady state 1 or steady state 0, ideally we know that pull down network or pull up network should be off. So there should not be any power consumption, but there are always leakages in any electrical circuit that will give rise to some power consumption even when the circuit is in a steady state. No switching is going on. That's called static power. But as we dig deeper into each of these, then we will know exactly why this thing is happening. But among these three sources or types of power consumption in any CMOS inverter or CMOS logic circuit, the first one, the dynamic power consumption, that is the useful power consumption. We have to spend it. Why? Because we want to charge or discharge the output node to produce binary ones and zeros. Every time we are charging a capacitor, discharging it, what we are doing? We are taking away energy out of the supply. So we are consuming power. That power consumption is required power consumption, is useful power consumption, because we need to charge and discharge the capacitor at the output to make the logic change, to use it as a logic circuit. On the other hand, any power consumption that is not contributing towards your binary operation, that is achieving 1 or achieving 0, those are unwanted power, parasitic power consumption. So short circuit power and static power are undesired power consumption. Ideally, if you can avoid them as much as possible or eliminate them completely, that would be good. So once again, those who came late. So today we are talking about different types or sources of power consumption in CMOS logic circuit. Among these three types, dynamic power consumption is the useful or required power consumption. We have to spend that power because of we need to charge and discharge the output capacitor to produce binary values. Short circuit power and static power, on the other hand, these are not contributing towards production of binary values at the output, so they are undesired power. So ideally, as a designer, if you can eliminate these two components of power consumption completely, that would be the ideal design. And ideally, if you can charge and discharge output capacitance with a smaller amount of energy, that will be your circuit will be more energy efficient. But practically, it is impossible to eliminate them. So what would be your practical target as a designer? You want to reduce all three. You want to be able to charge and discharge the output node, produce binary 1 and 0 with less energy, less power. So you want to reduce dynamic power consumption. You want to also reduce these two power consumption if possible. Reduce it as much as possible to all the way to the 0 if ideally. But let's say you have a total power budget for your circuit 50 watt. You as the designer, you want to spend as much possible of that 50 watt here. So you want to make sure that overall you want to lower power consumption, but your dynamic power consumption is much larger compared to this two. Or the other way, these two should be as small as possible compared to the dynamic power, because your total budget is 50 watt. From that 50 watt, if you drain 20 watt through short circuit and static power, you have only 30 watt left to do actually binary operation. So you as the designer, your number one target is to reduce all components of power consumption. Number two target is make these two weaker or as small as possible compared to this one, so that whatever limited budget you have for power consumption, maximum of it goes to charging and discharging the output node capacitors to switch the binary value from 1 to 0 or 0 to 1. So with that, now let's look at all the different components more in detail. So now, during the operation of any CMOS logic circuit, including inverter, what we are doing? We are applying an input signal. It can go from 1 to 0 or 0 to 1. If it is 0 to 1 or 1 to 0, then we will also getting charged or discharged at the output node. So during the charging and discharging of the output node, input itself is not injecting any current into the gate of this transistor or gate of that transistor because it's insulated. But there is an ideal assumption. Practically, even through the best possible insulator, there will be some leakage. We also assumed earlier that up to threshold voltage, the transistor is on, there is no current between source and drain, so transistor is off, there is no current between source and drain below threshold voltage. But practically, even below threshold voltage, there will be a weak current, there will be a weak channel present, weak current going from source to drain that will not contribute towards your binary output production because you are not using the circuit at that point. So that will constitute another source of leakage. So all these leakage will give rise to power consumption even when there is no output change. That is, circuit is in stable condition and those power consumption due to leakages present in any practical electrical circuit is called static power. And then we have to charge and discharge the output node when the transistor is on, and that power you need to spend or consume to charge or discharge the output node to produce 1 and 0, that is called dynamic power. So the total power consumption is static power plus dynamic power. However, from voltage transfer characteristics, we have seen that there is a direct path between supply and ground. At VIL, both transistors becomes on, and at up to VIH, during this transition time when it's making a high to low or low to high transition, both transistors are on. If both transistors are on, while you are charging and discharging, what is happening? So if both transistors are on during the transition time, from supply to ground, there is a short circuit or direct path exists. So while you are charging or discharging during the transition, not every current, every ounce of a current is going to this direction. Some of it will drain to the ground. That is a power you are consuming, unwanted power, parasitic power, which is not contributing towards charging and discharging. So that power consumption during the short transition period, when there is a short circuit or direct path from supply to ground, is called short circuit power or direct path power. In some literature, it is mentioned as PDP, direct path. In some literature, it is called as PSC or short circuit power, same thing. So the total power consumption of any CMOS logic circuit will be then static power consumption plus direct path power consumption plus dynamic power consumption. In this, as I mentioned, this is useful. These two are unwanted components. So we want to reduce all three components, but we want to reduce these two relatively at much lower level compared to this one. So whatever power budget you have, you want to spend most of it here, not here. So now let us look at the first one, the static power, or it is also called DC power consumption because it is present in IC at any point. Where this static power is coming from? Earlier we mentioned it is coming from leakages. There are two main sources of leakage, actually three main sources of leakage. We'll add the third one later. Number one source is called subthreshold conduction. When gate voltage is at or below threshold voltage, we are assuming that the transistor is off, there is no channel from source to drain. But physically, the channel does not wait for the threshold voltage to appear and all on a sudden the channel is formed. No. As you start raising the gate voltage from 0 and above, the depletion and inversion. Depletion means pushing down the holes downward and pulling up the electron. These two will happen almost parallelly. Yes, initially more hole will be pushed down, but very small amount of electron will start gathering due to the positive pull of this gate voltage. So there will be a weak channel present even below the threshold voltage. So at that point, source to drain, there will be a current. It's a very, very small current, fraction, like in exponential order, fraction of a current from the on current. So that conduction from source to drain is just draining your battery because you haven't turned on your transistor yet, you haven't applied your input yet. You apply input only when you turn on the transistor. So that is draining your battery. So that is the number one source of leakage. So static power means when the circuit is at steady state 1 or 0 at the output, you are not applying any new input. The circuit at steady state or DC state, but it will still continuously consume power, and that power is due to leakage current. and the number one source of leakage is subthreshold conduction between source and drain below the threshold voltage. That's why it is called subthreshold conduction, and it is the number one source of leakage in any digital logic circuit. 90% of the leakage current will come from subthreshold conduction. The second source of leakage in any integrated circuit at any point is called reverse bias PN junction. Inside the MOSFET structure, we have two PN junctions, one between source and body, another between drain and body. The way the voltage terminals or voltage polarities are decided in MOSFET, we make sure that this PN junction and this PN junction always remain reverse biased. They never get forward biased. If they become forward biased, then it will become short, current will flow in this direction instead of flowing in this direction, right? But if you, those who have taken semiconductor device physics class, when a barrier is present across a PN junction, it is assumed that the diode, the PN junction is off because there is a barrier. So the current is called a reverse bias condition. But practically, even through a reverse bias PN junction diode, when there is a barrier present, there is a small amount of leakage that flows in the opposite direction. That is called reverse saturation current or reverse bias PN junction current. That current will be very small compared to the on current of a diode, but that current in the reverse direction due to the presence of minority carriers in any PN junction device, that reverse bias current will be there. So when you are connecting it to battery, so this PN junction and this PN junction will continuously leak some power because of the presence of reverse bias PN junction current. That is the second most dominant source of leakage. That constitutes about 8 to 9% of the leakage current. 90% coming from here, 8 to 9%. And remaining 1% of leakage current is coming from gate leakage. Ideally, gate is insulated from channel by silicon dioxide, which is a very good conductor. But it's insulated with a very good insulator. But its insulation property is not infinite. It has some finite value. So it has a very high resistance, but its resistance is not infinite. So when you apply a gate voltage across it, this insulator will conduct some current, but that current will be probably 1/1,000,000th fraction of the real current. But still that current will be there. As we are making devices smaller and smaller, voltage levels are going down, overall power budget and current budget is going down. So if that gate leakage is, let's say, 1 microampere, if your total current is 1 ampere, compared to 1 microampere, it's nothing. It's 1/1,000,000, right? Or 10 million. But if your total magnitude of the current is 10 milliampere, then still you are having 1 microampere leakage. Now that 1 microampere gate leakage becomes much stronger because your overall operating current is now smaller because you are scaling down the device, you are scaling down the supply. So as we are going down the road of technology, making the devices smaller and smaller, supplies are coming down, this gate leakage also can no longer be ignored. So that constitutes the third source of leakage current. So 3 types of leakage current: subthreshold conduction, reverse bias PN junction current, and gate leakage current. All these 3 will contribute to power consumption during the time even when the circuit is in idle steady state. And that leakage will continuously go on, and that corresponding power consumption due to those leakages is called steady power consumption. So the total static power consumption will be then equal to effective supply voltage times the magnitude of the leakage current. Yes.
I did not understand the word leakage because of the gate. What you mentioned, why there is a leakage because of the gate side. Can you just explain?
Yeah, definitely. So yeah, this is our gate there, which is separated by this layer of insulation, silicon dioxide, and this is our channel. So when I'm applying a positive voltage in case of NMOS at the gate, body and the channel side is connected to ground anyway. So across the gate channel, this voltage is applied. So because this insulation, ideally there should not be current flowing in this direction out, right? Going in the draining to the body and ground terminal. But practically, this insulation means, a perfect insulation means resistance R is equal to infinite. But any practical insulator will have a finite resistance. Yeah, it can be very high resistance, but there will be a finite resistance. So even it is small, there will be a current I gate equivalent to VGS divided by silicon dioxide resistance. That current, which is probably 1 billion or 10 million fraction of a real device current. Okay. So this current here, VGS minus resistance of silicon dioxide, this current will be present no matter what insulator you use, because there is nothing called infinite resistance. Infinity is a concept. No practical value can be infinity, right? So that is the third component. But this component is very small compared to reverse saturation current. That reverse saturation current is very small compared to subthreshold current. Subthreshold current is very small compared to our on current ID. But as we are making devices smaller and smaller, supplying down, our project cost is limited, our total load current budget is very limited. So anything that is draining as a leakage current or leakage power, the impact is becoming more prominent. When we started with the IC with 10 volt supply, 1 watt, 2 watt of leakage was not affected. Then we came down to 1 volt supply. So that 1 watt or 2 watts of leakage is becoming a dominant factor because supply is going down, power budget is going down. So at this point, introductory level, we are assuming that we will have a fixed amount of leakage in any device. So if I want you to solve any problem to calculate static power, I will give you the magnitude of the leakage current. Practically, analyzing and understanding leakage sources and mechanism, you can spend your entire career on it. Then there was a guy, there is a man called Dr. Kaushik Roy. He is a godfather of leakage current in Purdue, West Lafayette. So some of his students are now faculty at MIT Berkeley, and all he does, he analyzes subthreshold behavior of transistors. And that is very important because that gave rise to an area called ultra low power nanoelectronics. And there, initially there are a couple of other researchers like Carnegie Mellon, his name is Larry Pilevi, and all those people, they are working on ultra low power microelectronics. These people initially they were doing research on how to handle and minimize leakage in micro or nanoelectronic circuits. Then they're now working how to utilize that subthreshold leakage to develop ultra low power microelectronics. So at this point, we are not going to go that direction, we are just going to say that there will be finite amount of leakage, and for that there will be finite amount of static power consumption. Okay. So now so in the static power consumption, as I said, at this point we will assume that at a given technology for a given supply, we will have a fixed amount of leakage current out of every device or every circuit, and we will multiply that fixed amount of leakage current with the supply voltage to calculate the static power or DC power. At this point we are assuming that it's a constant DC power. Power is voltage times current. So the VDD is the supply voltage, leakage is the current, but practically that leakage current will have some variation, but we will ignore that. The next one we want to talk about is the short circuit power or direct path power. As we mentioned, you can see in the voltage transfer characteristics, forget about whether NMOS and PMOS is linear saturation. From point A to point B, from VIL to VIH, during that time transition, both transistor MP and MN are on. So there will be a direct path present or short circuit path present from supply to ground, and that current is called short circuit current, and that will drain some power out of the battery. That power is called short circuit power. Now we want to now try to estimate how that short circuit power will look like, or what is short circuit current. So at point A, up to that, one transistor was off, the other was on, right? And then one transistor remains at saturation, the other one linearly goes up. At VM, both transistor reaches their highest current, saturation, and then one transistor remains at saturation, other transistor linearly goes down, and at VIH, one transistor goes off, the other one gradually linearly goes down and becomes off, right? So let's draw a line here. This is my short circuit current pulse. Up to VIL in the voltage card, voltage transfer characteristics, there is no short circuit power or short circuit current because one transistor is off, the other one is on. At this point, both became on. One at saturation constant, other one is linearly increasing. So the current will continuously increase. Short circuit current, you can see it from sharply rising, decreasing VTC, right? So when the current will peak, when both transistors reaches saturation at VM. And from there, one remains at saturation, other one will linearly go down. At one point, that one at saturation become off, and the other one will be going down to zero. But at one point, this point, corresponding to VIH, short circuit current will be turned off because one transistor is off. Short circuit means short circuit from supply to ground. If one side is disconnected off, there is no short circuit. So during the transition time from VIL to VIH, we will have a short circuit current pulse like this. Practically, it will not be linear like this. It will be slightly non-linear. But for simplicity, we will assume that we will have a triangular pulse starting from VIL, going peak at VM, and then again going down, becoming zero at VIH. So this is the pulse, the nature of the short circuit current we will see during that transition. What we are trying to estimate is, due to the presence of the short circuit current or direct path during the transition, how much power will be draining out of the battery. That power is short circuit power. That power is direct path power. So to calculate power, what we need? Voltage times the total current we have taken out of the battery or leaked from the battery during the short circuit time. So now you have to remember, the signal we are talking about, input or output, it is going up and down in one complete cycle. So during up of the input and output, we will have one short circuit pulse like this. As again it comes down, you will have a reverse transition, you will have another short circuit period, so you will have another short circuit period here. So in one clock cycle, this plus this will be the total amount of current that is coming out of the battery due to the existence of the short circuit or direct path. So if we can calculate the total current drained out of the battery multiplied by total supply voltage, we get the total energy taken out of the battery during this complete one cycle due to the existence of short circuit path. If we know the total energy taken out of the battery during one whole clock period due to short circuit path and multiplied by clock period, energy per time is power, right? So that's what we are heading to. So now, total energy taken out of the battery due to the existence of short circuit will be what? For simplicity, let's assume that this is a perfect linear up and down. So, and let's say the total, the peak of the current during the short circuit period is I peak. And this from beginning to end of the short circuit current pulse, let us assume that the timing, the period of the short circuit pulse is TSC. So each side will have a short circuit current pulse of with TSC in time scale, and its peak value is I peak. Now we want to calculate the total current taken out of the battery during the short circuit period. So now, we have a rectangle, is actually two triangle. The height is I peak, total base is TSC. So what is this? TSC divided by 2, assuming that it is symmetrical linear. So now, first, if I can calculate the area of these two, this one multiplied by 2, I get the total area, right? So area of this one is what? Half times height times base, right? This is just this half triangle, right? Now, if I multiply it by 2, I get the total area of this triangle on upward transition. But in one complete clock cycle, I have to also think that there is another cycle that is going down, so I have to multiply it by 2 again, right? So this is the total current, short circuit current. Now I have to multiply this with VDD. That is my total short circuit energy taken out of the battery during this entire clock period due to the existence of two short circuit pulses, right? So that is what I have written here. So now, so here I have 1, 2 here, cancel, right? So the total energy, short circuit energy taken out of the battery due to the direct path is VDD I peak times TSC. TSC is the length of the short circuit pulse on each side. It is the peak value. Now the power, short circuit power is what? Short circuit power is energy per unit time. This energy we have taken in one clock period T, so divided by 1 over T is what? Frequency of the circuit, right? So ESC times frequency. Now, ESC we found that is VDD I peak TSC, right? So VDD I peak TSC times F. Now, what is current times time charge, right? Q is IT. So the total charge taken out of the battery, QSC, during the short circuit period. So I improved it because these two are unknown, right? And we are trying to get value of short circuit power in terms of known quantity. Now the charge Q is what? Q is CV. Charge Q is CV. V we know it is VDD. That's what we are talking about. C will be the effective capacitance of the device during the short circuit period. So you have to know what are the capacitance effective. So I am replacing Q with CSC VD. Now there is a VD, so it will be CSC VD square F. I know my frequency. I know my supply. If I can get a way to calculate effective capacitance during the short circuit period, I know what is the short circuit power consumption for a given frequency for a given device. So now, from here, again, these formulas should not be used to calculate actual power. This tells us the design dependency. What does it tell? You as the designer, if you increase frequency, your unwanted short circuit power consumption will increase linearly. If you increase supply voltage, power consumption, short circuit will increase quadratically because there is a square dependency. In the reverse, if you slow down your circuit, reduce the frequency, you will get a linear reduction of short circuit power. But if you can slightly reduce your supply voltage, you will get a quadratic reduction of power supply. So you see that there is, so now as a designer, you have three parameters to play with. Device size and dimension to set the effective value of capacitance. Remember all the internal capacitance of the device. Circuit and device sizing to set the value of capacitance. Frequency selection and supply voltage selection. Among these three, supply voltage reduction will have the most prominent effect on the energy efficiency. If you can reduce your supply voltage slightly, that will give you a quadratic savings in terms of power consumption. Now, if we look at the previous slide, static power has a linear dependency on supply. So if you reduce supply voltage, it will reduce static power consumption linearly. But it is a very simplistic assumption right now. So we got the short circuit power. Now let us look at the dynamic power. This is something we cannot avoid because we have to charge and discharge the output node to produce the desired binary value at the output node. So it's a useful power, but we want to charge and discharge with as small power as possible. But to make the decision, we want to know what are the factors that will determine the dynamic power consumption. So first, let us assume that our input is 0. That means PMOS is off. Sorry, NMOS is off. Out of the picture, PMOS is on. Supply will be charging this output node to make a 0 to 1 transition to produce binary 1. So now, in this condition, now let us see how much energy we are taking out of the supply. There is a charging current, ID of T is a time varying current that is coming out of the supply, charging this load capacitance. So the total energy will be integration of instantaneous power. Instantaneous power is current at any given time T times supply voltage, right? So ID of function T times Vd, if we integrate it over time, at this point 0 to infinity, all is infinite, all the way up to it's going down. So now we will replace that infinity sign because right now we're just saying it is an indefinite variable. That is the total energy, total current multiplied by voltage, total energy taken out of the battery for charging this load capacitance. But this current is going into a capacitor. We know that capacitor current is, if it is load capacitance, CL dV over dV out. dV out over dt, right? Current, capacitor current IC is C dV over dt. So here the voltage is V out, here the capacitor is load capacitance, right? So we know, and it is a positive current, it is charging, voltage is going up, current is charging, so there is no minus sign. So CL dV out over dt times dt, VD is a constant, we take it out of the integration. So now V out, now we can take out that infinite sign, because what is the initial value of V out? 0. As we finish charging load capacitance CL, final value will be VDD. So my limit of integration will be 0 to VDD for V out, right? So that integration gives us that the total energy taken out of the supply VDD is equal to CL VDD square. There's the, now the question is, next question, well, for charging this load capacitance and making a 0 to 1 transition at the output, we have taken CL times VDD square amount of energy out of the battery. The question is, did the entire amount of that energy taken out of the supply is stored here? The answer is no, because while I am charging, it is also passing through a PMOS transistor which has a finite on resistance. So it will consume power equal to I square R, or VR times I, the voltage times the current that is flowing through the resistance, right? So now let us see how much we have taken out this energy out of the supply. Some of it spent by this PMOS transistor because of its resistance, and it is dissipated as a heat. We lost it. We only have whatever we have stored across the capacitor. If we can calculate what is stored across the capacitor, from that total energy, we know how much we spent here for charging and discharging. That is part of my dynamic power consumption, right? So the energy stored across the capacitor, again, it will be, what is the capacitor voltage? It is a variable voltage V out. Because initially it was 0, it is going up. The current through the capacitor is a variable current IT of T. So a variable current injecting charge into the capacitor, and it has a variable voltage across. So the total energy injected into the capacitor will be integration of current times that voltage, right? So integration of ID of T, current going into the capacitor, multiplied by V out of T, the voltage effective across the capacitor. Again, ID of T we can replace by CL dV out over dt. So what we have now? We have CL dV out dt into V out equal to, now V out we know it is starting from 0 going to VDD. So now if we now do the integration here, then result is CL VD square divided by 2. So we have taken this much energy out of the battery, and at the end of charging this voltage at the output node, the capacitor is holding this amount of charge. Where did the other portion go? The PMOS transistor spent it. Energy consumption by the PMOS transistor, that will be total power taken out of the supply minus the energy stored in the capacitor, there will be CL VD square divided by 2. Now, during the next phase, the next half cycle, when input becomes 1, NMOS will be on, PMOS will be off. So during the second half of the clock cycle, now this output will be discharging to the ground through NMOS. So whatever it has stored, that half CL VDD, that energy will be eaten by whom? The resistance of the NMOS, and it is draining to the ground. So the energy dissipation by the NMOS during the discharging will be exactly equal to the energy we have stored in the capacitor. So the total dynamic power consumed by the charging and discharging will be energy consumed by the PMOS while charging, energy consumed by the NMOS while discharging. And from energy conservation law, that total has to be equal to the energy taken, right? And it is true. So the total dynamic power is NMOS power consumption plus PMOS power consumption, that is CL VDD square divided by 2. That is total energy. But this energy we have consumed for charging and discharging in one clock period. So the power consumption must be divided by T. It's per unit time. So the dynamic power consumption will be CL VDD square times frequency. So from this equation, we can also now conclude that you as the designer, to set the value of dynamic power consumption within the budget given to you, you have 3 parameters to play with. Load capacitance, that will be dictated by the size of the device and the wiring and their size, supply and frequency. Among these 3, this is the dominant factor that will determine whether you have a higher or lower dynamic power consumption. So if we now combine all these 3 components, what we have? The total power consumption in your integrated circuit is static power plus short circuit or direct power or dynamic power. Decays times VDD plus the. So now from this equation, as you can see, 2 out of 3 components of power consumption are dependent on supply voltage in quadratic relation. Frequency has a linear, and frequency doesn't have an impact on leakage current. So leakage current will be there independent of what you do with the frequency. It will be omnipresent. It will always leak at a certain amount depending on the physical voltage and material parameter of the circuit and device. So it will, as of now, at the introduction level, leakage is independent of frequency. Short circuit power and dynamic power are linearly dependent on frequency. Leakage, static power is linearly dependent on supply. Short circuit and dynamic power is quadratically dependent on supply. So from this equation, you as the designer, if your ultimate goal is to achieve maximum possible energy efficiency, the very first thing you look at, can I reduce the supply voltage? Because then it will give you quadratic reduction here, which is the important and the desired component of power consumption, which is also give you quadratic reduction here and linear reduction here. So that's why there is a continuous push to go towards from low power design to ultra low power design. So today, most of the microprocessors we use, they operate between 0.9 to 1 volt supply range. They are not able to go below 0.9 because then the speed actually we have to sacrifice. So now, let me now compare this slide with this slide. Here, propagation delay Tp, as you can see, the propagation delay Tp is the indication of speed. So let me write it here. So propagation delay Tp. So from this lecture, what we can conclude? You as the designer, you want higher speed, you want energy efficiency, right? So your speed is determined by Tp, which is proportional to 1 over VDD. Your energy efficiency is determined by power consumption, which is proportional to VDD square. 2 out of the 3 terms proportional to VDD square right now. So higher speed dictates I have to lower the propagation delay, right? You want higher speed. I have to reduce the propagation delay. To reduce the propagation delay, I need a higher supply, right? Because it's in the denominator. However, I also want higher energy efficiency. That higher energy efficiency means that I have to lower power consumption. But for lowering the propagation delay, if I increase supply voltage, it will increase power consumption quadratically, leading to significant reduction of energy efficiency. So the higher speed requirement and higher energy efficiency requirement, these two are conflicting goals. So you want to get maximum in one direction, then you lose the other. That's why in IC design, they will never give you one target. They will give you power, delay, product. Power, delay, product. It is power consumption times propagation delay. That is the budget you have. Your power delay product should be less than, let's say, 100. So you have to now find an optimum path. Should I sacrifice on the power side for higher speed, or should I sacrifice on the speed side too? That's why in any commercial circuit, like any day-to-day circuit, we never implement any design for the best possible scenario in terms of energy, efficiency, or speed. We always find a middle ground. It's a sacrifice, it's a trade-off. So it's an optimum design. But for now, let me give you kind of an overview of where we stand now. So let's draw it an XY quadrant. This is delay. Typically, we write power here. This is power. This is delay. So now, as we mentioned, if we want to sacrifice this, we have to lower the delay, we have to increase the power consumption, or vice versa. So currently, we are stuck here in mid power and mid energy range. However, actually it is written in speed. Sorry. So here it's called mid power, mid speed. So one direction of research is going in this direction. It's called ULP range, ultra low power. Power is very small. Speed is not at all a concern. We want to lower the power consumption as much as possible, because the circuit that we are going to design will have very low speed. Like the pacemaker example I gave you, they are not operating even in kilohertz, they are operating in hertz, 50, 60 hertz, right? So that is called ultra low power range of operation. So there is a huge new area of research going on for last 2-3 decades, devices and circuits and applications for ultra low power range. And then there is another new areas, it's not new, several decades old, it's UHF range. It's called ultra high frequency range, where your ultimate requirement is high speed and precision. You are operating in the terahertz or hundreds of or tens of gigahertz. Power consumption, these are highly specialized application, defense or satellite communication or space communication. The speed and the accuracy is more important than the power consumption. So, but for that you have to sacrifice power. So what is the utopian world? Utopian world would be if I can move here. Right? Ultra high speed with ultra low power. If we can move that direction, in this direction, that would be a world where everything will be superconducting, right? So, but whatever was kind of a wild imagination 50 years ago, now, 50 years ago, those science fiction became reality now, right? We are now talking about holographic cell phone. You type, you see the screen in the holographic image, right? About 10 years ago, they tried in Oscar for the first time. There was a British singer. She was barred from entering USA because of her drug allegation to accept Oscar. She received an Oscar for one of the musical movies, for her voice in one of the musical movies. But she was barred at that time because of her drug abuse to enter to USA. So they gave her the Oscar. That was the first holographic test. She received that virtually in London, but everyone in Kodak Theatre, they saw her physically on the stage, Oscar stage, receiving the, so it needed 64 cameras to over there and 64 cameras over there to create that holographic image. A person who was sitting or standing on a stage in London, but the whole audience and the whole world saw her on the Oscar stage in Los Angeles, Kodak Theatre. So now, at that time it was very challenging. Now they're saying that it will be, you will be basically typing on your thumb and a screen will show up on the air. That is holography. So those science fiction will become reality, and it is becoming reality. So this is where, but as a designer, so what should be our goal? Yes, we don't want to stay here. There will be some operation will be here. There will be some operation embedded electronics in vivo devices will be here. But in general, our personal and commercial design space, if we can move this in this direction as much as possible, we get higher speed and lower power consumption.
I'm assuming that's where some of our future technologies like graphene.
Yeah. So now they are exploring all the different materials. So the now latest choice of physicists and engineers are a group of 2D nanomaterials and alternate technology like negative capacitance field effect transistor or TFET or narrow-wire FET at the device technology, alternative to MOSFET or CMOS at the device level, and at the material level, alternate to silicon, magnetic material, 2D nanomaterial that are explored. They are thinking that they will give us application here, here, and move this thing to this direction. So that's basically the motive for all the futuristic research. So with that, I think we are end of this lecture. So I do not want to burden you with the new topic today, so I will leave it here. So what it looks like, most likely lecture 4 and 5 will be done within next 3 classes. So between, as we finish lecture 5 and the midterm, I will not introduce any new topic. I will basically go through all the lectures and we will be solving lots of problems from lecture 2 to lecture 5. Okay? So please start preparing mentally for midterm. It will be one
This is the
hour,
IEEE.
30-minute long exam covering lecture 1 to 5.
Give me one.
Is there any quiz or something before the midterm?
Oh yeah, there will be at least 2 quizzes before the exam to prepare you for, and the TA will be uploading 4 practice homeworks. So the exam questions will be exact replica of homework questions and the quiz questions. So by attending all those quizzes and solving those homework problems, you exactly know what type of questions to prepare for. Yes.
Like quiz and answers, are those posted in Canvas or will they be posted in Canvas? Like the answers to the quizzes?
I thought he already posted, but I will double check. But he is
I
supposed
actually, I haven't checked in a
yeah,
while, so.
he is supposed to
For the
post.
first quiz, it is posted already.
Oh, okay. Yeah, because I told him to post everything. Okay. See you.
Okay, for anybody who wants to come to the event on Monday with Dr. Farhan Ashik, here's some QR codes you can scan if you want. If you want to join the IEEE group. We are going to be handing out official certificates for people who attend that event if you're an IEEE member, which is $16 right now.
16?
Only $16 for students.
So how many hours this training is for?
Huh?
For how many